In the last class, I was talking about composite functions and chain rules. So I already explained you the chain rule, and we saw one more thing, the invariance of differential. That means if f is a function of u and v are indeed functions of x and y, then if you find the differential of f using u and v, and if you find the differential of f using x and y, both will be same. So this is what will be very much important for doing few sums. So let me start one sum like this. So the question is, transform the equation. So I want to transform the equation. What is the equation? This is the equation: y dz dx, sorry, del z del x minus x del z del y, that means z is a function of x and y, equals to y minus x times z. So I have this equation. This kind of equations are known as partial differential equations. You'll be learning this in your 6th semester course. So I want to transform this equation by introducing new independent variables u and v. So what is u? U is x square plus y square, and what is v? V is this 1 by x plus 1 by y, and the new function, there is no dependent variable, w equals to log z minus x plus 1. So I will tell you what you are supposed to do here. See, initially what I have, z is a function of x and y, and z satisfies this equation. That means z is a function of x and y. So z is the dependent variable, x and y are independent variables. So I have this complicated looking equation, right? So I want to transform this equation by introducing new variables. So instead of using x, I'll be using u. Instead of using y, I'll be using v, where u and v are both functions of x and y. And instead of using z, I'll be using w. So how they are related? U is a function of x, y, v is a function of x, y, and w is a function of x, y, z, because z also depends upon x and y. So eventually w is also a function of x and y. So my point is this: you have to replace x by u, y by v, and z by w. In this equation, if you replace z by w, y by v, x by u, then how will this equation look like? Okay, so let's start. So what is the procedure? I'll tell you how to solve this kind of question. So solution. So the aim is to transform this equation into a new equation which contains u, v, and w only. Let's see how to start. So u is what? X square plus y square. You find the differential of u. What is differential of u? Du equals to del u del x dx plus del u del y dy. Do you agree with me? This is the formula for differential. So u is a function of x and y. So differential of u, du, is given like this. Let's compute du. What is du? Let's see. What is del u del x? Differentiate this partially with respect to x, 2x dx. And what is del u del y? 2y dy, like this. So this is the differential of u. This is the differential of u. Similarly, let's find the differential of v. Let's find the differential of v. And what is v? So v is 1 by x plus 1 by y. So this time I will not write the formula for differential. So what will be the formula, you know? So dv will be, first differentiate partially with respect to x. So minus 1 by x square, and then we write dx, and then plus partially differentiate with respect to y. That means minus 1 by y square dy. I hope you understand what is how I calculated dv. And similarly we'll find dw. Now you see w is a function of kind of three variables, z, x and y. So the formula for differential will be extended. So what is dw? It is del w del x dx plus del w del y dy plus del z, del w del z into dz, because w depends upon z, x and y. Eventually it is a function of two variables because z is dependent on x and y, but I am writing like this. So what is this? Put the value. So what is del w del x? That means you want to differentiate w with respect to z, with respect to x. So what is the differentiation of this with respect to x, keeping everything else constant? So only minus x is there, rest all are constant, so differentiation will be 0. It will become minus 1. So minus 1 dx plus similarly differentiation of this with respect to y, that is minus 1 dy, and differentiation of this partially with respect to z. So differentiation of log z will be 1 by z, their differentiation will be 0. So 1 by z dz. Or let me write one more line just for simplification. Or dw equals to minus dx plus dy plus 1 by z dz. So did you understand up to here? So you always remember how to start this kind of questions. You always find the differential of the new variables. That is the first task you have to do. So I am done with du. This will be required a bit later. I'm done with dv. This will also be required, and I'm done with dw, which will again be required a bit later. So remember one thing, you always start like this. You differentiate, you find the differential of u, differential of v, differential of w. Now let's see what to do. Now what I want w to be function of u and v. Remember, I have introduced new variables u, v and w, and I want w is a function of u and v. Like initially z is a function of x and y. I want to replace x by u, y by v and z by w. So what is my target? I want to replace w by w will be a function of u and v, that I want. So I'll just write that thing. So now w is I want w to be a function of x and y. W is a function of u and v. So therefore let's find dw in terms of u and v. So if w is a function of u and v, what is the differential of w? It is del w del u du plus del w del v dv. Do you agree with me? Because w is a function of u and v. So I can also find the differential of w. In terms of u and v. Right? Now you see, I don't know what is del w del u. Okay. But I have already computed the value for du. So what was the value of the quantity du, differential of u, computed in the last page? So the value was 2x dx plus 2y dy. So this was the value of du plus del w del v, and what was the value of dv? I forgot. So the value was minus 1 by x square dx minus 1 by y square dy. So minus, you may please check and verify. Okay, this is already computed in the last page. So again I'll repeat what I am doing. I am computing w, I am computing dw, I am computing dw, that is differential of w in terms of u and v. So this is the formula for differential, you know. So I have the value for du, I have the value for dv. I hope you have no problem up to here. Now your task is to take all the dx together and take all the dy's together. That means from here what is the value for dx? 2x del w del u, this is the value for dx from here, plus minus del w del v into 1 by x square, this is the value of dx, so I am taking dx common. So this is my value of dx plus, let's take all the dy's together. So this from here dy will be obtained. So plus 2y del w del u minus del w del v into y 1 by y square dy, and this is the value for dw. Do you agree with me? So let me call this some equation 2. I'll mark some equation 1. Let me call this as equation 1. Okay. So now here we will use the fact that the differential remains invariant. We have proved this one. We know that differential remains invariant, so we'll use this fact. What I'll do? So 1 and 2 are invariant. I know this fact. The value of the differential that I have obtained using x and y and the value of the differential of w that I have obtained using u and v, both must be same as done in the previous class. The differential remains invariant. So 1 and 2 are invariant, therefore I'll put the value of dw and this value of dw must be same. So what was the value of the dw computed in the last page? It was minus dx plus dy plus 1 by z dz. This was the value of the differential of w, and from here this is the value of the differential of w. I have to write a lot. Okay. Be very careful while copying everything. So both of these quantities are invariant because this is also the value of dw, this is also the value of dw.
So
yes.
minus 1 by square.
Okay. Sorry, no. Yeah, thank you. This is the minus. Okay, what next? I'll tell you what next. Very easy. Now what you do? You just make dz as your subject and send this dx all together and again obtain something new. You see what happens. So what I will get here? 1 by z dz. I will not write 1 by z. What I will do with 1 by z, I will tell you. So what is dz? I will send this minus dx on the right hand side. So this will become plus dx. Again I will take dx common. So what will I remain with? 2x del w del u minus del w del v 1 by x square, and this minus dx will come here and become plus dx, so it will become plus 1 dx plus, similarly here minus dy will be sent to the right hand side. That means 2y del w del u minus del w del v 1 by y square plus 1 dy. So this is the value of 1 by z, no? 1 by z. So I'll send this z here also. So here it will be z, here it will be z. So what I have done, I have obtained dz. Am I clear? Now again I'll use the fact that z is actually a function of x and y. Z is actually a function of x and y, so I can find the differential of z in terms of x and y. Let's see how. So this is also the value of dz that I have obtained. Now I know that z is a function of x and y, so dz can be written as del z del x dx plus del z del y dy. So this is suppose 4, some 4. So what I know, 3 and 4 are invariant, right? Because 3 and 4 are invariant. So I can put the value of del z dz on the right. Okay. What I'll obtain, del z del x dx plus del z dy del y dy. So just look here what I'm doing. So what I know, this is a z is a function of x and y, so I can find the differential in that manner. This value of differential and the previous value of new value of differential both must be same. So I'm putting here dz and I have to write whole of this. So start writing. Be very careful. So what you can do, you can multiply by z also. What will remain here if I multiply by z also? So we remain here with 2xz. Please check. Okay. 2xz del w del x minus z by x square del w del v plus z, because I'm multiplying z to each of these terms, dx. I'll try to fit somewhere here. Okay, plus I'll write everything again in terms of y. So it is what? 2yz del w del x minus z by y square del w del v. Sorry, this will be u, no? This will be u. So sorry, no? This will be u if I'm not mistaken. Yes, no. Hold on, let me please check. So this all are u and v. So u plus z d. Am I clear? So just compare. So this dx plus this dy equals to this dx plus this dy. So compare. This is the value for del z del x and this is the value for del z del y, because dx dy dy. Just comparing. So what will I get? I'll get the value of del z del x like this. It is 2xz del w del u minus z by x square del w del v plus z. So this is the value for del z del x and this is the value for del z del y. So what is this? 2yz del w del u minus z by y square del w del v plus z. Am I clear up to here? So I will explain the whole process very quickly. So what was my aim? The given equation was in terms of x and y, and z was a function of x and y. I wanted to transform this equation in terms of new variables u and v, and w as a dependent variable of u and v. Okay, so I have to replace x by u, y by v, and z by w. How I started? I first calculated the differential of u, the differential of v, and the differential of w. Okay, using the given formulas. Then I know that w is a function of u and v, so I again computed the differential of w in terms of u and v, because I know that the differential remains invariant, right? So what I did, I equated both the values of differential of w. Then using that thing, I got the value of differential of z, but again I know that z is a function of x and y. I computed z in terms of x and y, dz in terms of this one, differential of x and y, and then I equated. And then on comparing, I have the value for del z del x and del z del y. Now what I will do, I have not used this equation. Now I will use this equation. In this equation, I'll put del z del x and del z del y that I have obtained. So let's see what happens. Okay, so what I will do, I will now write the original equation which was given initially. So now what was given to us, the equation was, which equation I wanted to transform? This equation. So the use of this will be at the end. So del z del x minus x del z del y equals to y minus x z. So what I'll do, I'll put the values of del z del x, which is like this. Let me put the value for del z del x. So it is 2xz del w del u minus z by x square del w del v plus z minus, it will not fit here, I'll write here. Okay, so minus x into del z del y, so 2yz del w del u minus z by y square del w del v plus z. So this equals to, right hand side remains as it is. So I'll just, the values obtained from here, del z del x and del z del y, I am putting here. And now your task is to simplify this complicated looking thing, and the simplification is not that difficult. Let's see what happens. If I multiply this term by y, so what will this become? 2xyz del w del u minus 2xyz del w del u. So these two are getting cancelled. That's a good news for us. These two are getting cancelled. What I'm remaining with? Minus zy by x square, and from here what I'm getting? Minus minus plus zx by y square del w del v, right? So from this term and from this term, these two are getting cancelled. This term and this term are remaining, and what I'm getting? Minus, sorry, plus yz minus xz. There is a minus here. Plus what I'll get? Plus, if I take z common, what I am remaining with? Y minus xz. Do you agree with me? And the things are very much clear now. These two are getting cancelled. So I am remaining this quantity equals to 0. Assuming that this is not 0, so what I'll get? Del w del v equals to 0. This is your transformed equation. So the given equation is equivalent to this equation, del w del v equals to 0. So you see, this and this is getting cancelled. So I am remaining this quantity equal to 0. Assuming this is not 0, this is not identically 0 definitely, and I can equate that to, this cannot be 0 for all values of x, y, z. So only this should be 0. So you see, the complicated looking equation, which is not that easy to solve, you have to use something called as Lagrange's multipliers that we'll learn in the 6th semester, has been now transformed to a very simple equation. You'll see that this equation is very easy to solve. So this is the advantage of transforming the equation. Am I clear? I will give a homework of similar kind. Okay, actually these are not that important. I'm just explaining like this. I have to teach a new topic, but I want to do few sums. Okay, so anyways, I'll give this kind of sum as your homework. I'll do one more sum of this kind. So another type of question, I will not do the similar type. Similar type will be a homework because the process is very simple. Another one is this. Yes, number 2. Show that f of xy comma z minus 2x equal to 0 satisfies under suitable conditions the equation x z del x minus y del z del y equals to 2x. What are these conditions? Okay, so what they have said, you prove that this function, so I have some function in terms of xy and z minus 2x, this function will satisfy this equation. So when you learn partial differential equations in your 6th semester, you will see you have to find this solution. This will be given to you, you will show that this is the solution. But now we'll reach from here to here because we don't have the concept of partial differential equations now, how to solve a partial differential equations. So what we do, we'll reach from here to here. I want to prove that this function is dependent on xy and z minus 2x. This function will satisfy this differential equation, this partial differential equation under some suitable conditions. So I will prove that first that this satisfies this differential equation under some suitable conditions. That means if I put, okay, anyways, and what are these conditions? We'll see that. What are these conditions? We'll see that. Let's see how to start. Call this as u, call this as v. Okay, so let u equals to xy and v equals to z minus 2x. Okay, now, so I'll replace u's by x by u, y by v, and then f is your new function. See, initially the new functions were, the initial functions were z, x and y. So z is a dependent variable dependent on x and y. Now I have u and v, and f is dependent on u and v. So this is my aim, just like the previous case. There it was uvw, here I have fuv. So again we'll start in the same manner. Let's find the differential of u and the differential of v. So let's see what is differential of u, du. So del u del x, which is y, because if I differentiate this with respect to x partially, y is a constant, y goes out. What is the differentiation of x? Is 1. So this plus del u del y, which is x dy. Did you understand my point? Similarly, what will be dv? So it is del x, del v del x, that is minus 2 dx, del v del y dy, but del v del y is 0 because there is no term containing y, so that is 0, no to write, and then del v del z, that means is 1 dz. So I have du, I have dv. Now what I have, f of uv given to be 0. That I am not saying, it is given in the question. F of u comma v equals to 0 because this is u, this is v. Now f of u comma v is 0. That means the differential of f will be 0 because this is a 0 function. If you find del u, if you find del f del u dv, du plus del f del v dv equals to 0. So therefore the differential is also 0 because if the function is identically 0, its differential is also 0. Use the formula, and get it. Now let's see how can we find del f. What is df, not d, del f, df. How to find df? It is del f del u du plus del f del v dv equals to 0. Did you understand my point? If the function is identically 0, its differential is also 0. And how to actually compute differential? This. Because this is 0, I know. Who can tell me what will be the next line? What to do in the next line? What we will do, as we had done in the previous case, we'll put the values of du and we'll put the values of dv. So let's put it. So del f del u du. Please write your del and d clearly. Okay. So what is du? Let's put the value of du. Y dx plus x dy del f del v. What is this? Minus 2 dx plus dz equals to 0. So again the same logic. What I'll do, let's multiply everything and try to make dz as your subject. I'm following the same process as I did in the last case. What I'll do, I'll try to make dz as my subject and set everything on the left hand side or right hand side. I'll put what I have, del f del v dz, okay, good enough, this into dz equals to, I'll send everything on the right hand side. So if this goes to the right hand side, what I'll remain with, 2 del f del v dx, and this will again go to the right hand side, minus y del f del u dx. So this goes on the right and becomes plus, this goes and becomes minus. I'm taking dx common, and minus x del f del u dy. Yeah, this is the thing. So this dx minus this dy. Am I clear? So what Rajkamal said is exactly true. What I was doing, I will again find dz in terms of x and y, and that will remain invariant. So what I'll do, I'll simply put the values without writing much. So del f del v dz. So what is dz? I know the value for dz. Dz is, because z is a function of x and y, so del z del x dx plus del z del y dy equals to, you have to write this whole thing again, which is very complicated. Be very careful while writing. Dx minus x del f del u dy. Again the same thing, I'll send all the dx on the right hand side, or basically I'll compare. Let's see what happens. So what next, as you can see, let's compare the values of dx. So what is the value of dx here? What is multiplied in dx here? This quantity, and this quantity is multiplied here in dx. So both these quantities must be same, and what is multiplied in dy here? This into this, and this will be equal to this. So let's equate that. Somebody please write. So this will be equal to this on comparing, and this will be equal to this. So let's compare the coefficients of dx and dy. So I'm writing, please check what I'll get. Del f del v into del z del x. This I should get. This is the coefficient of dx on the left, and the coefficient on the dx on the right is this, del x minus y. Please check once if I make a mistake. Del u, and what I'll get, the coefficient, so del f del v into del z del y equals to minus x del f del u. No? Yes. In the original equation, what was the equation which I have not used here up to here? I need the values of del z del x and del z del y. So let's compute the values of del z del x and del z del y from here. So therefore, what is del z del x from here? We are actually dividing by del f del v. When I am dividing by del f del v, what I'll get here? So 2 del f del v divided by del f del v. But when I'm dividing, I'm assuming that this is not 0. That is my required condition, which they have asked in the question. So what is the condition that I'm assuming? I'm dividing by del f del v, so I'm assuming that del f del v is not identically 0. So this gets cancelled, minus y del f del u divided by del f del v. I have this, and what is del z del y? I'm getting minus x del f del u divided by del f del v. What condition I am assuming? Provided I am assuming that del f del v is not 0, because if it is 0 I cannot divide, as simple as that. So this is the suitable condition which we want, okay, about the function f. Now almost done. I want to prove that this will satisfy this. So instead of del z del x, I'll put the value what I have obtained. Instead of del z del y, I'll put the value what I have obtained, and I have to bring 2x. That is what is meant by satisfies, right? I'll start from here. So now what I have, the equation x, what I have the equation x del z del x minus y del z del y. Let's see whether I get 2x or no. So x, put the value of del z del x to this value, I'll put this value, right? 2 minus y del f del u divided by del f del v into, right? You can not in whole divide, so you can use a bracket if you want to, minus y. So minus minus will become simply plus. I'll write here x. I'll simply remain with del f del u by del f del v. And you can see here I'll simply get with 2x. Yes or no? Because if I multiply this by x, this will become xy in minus this thing, xy in plus this thing. These two got cancelled, and simply remain with x into 2, which is 2x. Okay, thus so f actually satisfies this equation, because when I started with f, I am getting this as 0. The equation is satisfied. Thus f satisfies the given equation provided. So one thing we have assumed like this only, provided f is differentiable. Why are we assuming this? Because we have used chain rule. We have used the concept that the differential remains invariant. All these conditions will only hold when f is a differentiable function. Keep that in mind. While doing the proof of chain rules, or look at the statement of chain rule, I have already written that f is a differentiable function. All the time I have written this. If f is not a differentiable function, I cannot talk about the chain rules. The chain rule may not be valid. Okay, so f satisfies the given equation provided f is differentiable and the partial derivative of f with respect to v, I can also write like this, is not 0. So under this condition, f satisfies the given equation, and yeah, so f is differentiable and this is not 0. Do you want to ask anything? One last thing. So this much for today, and one more thing, I'll not be doing this kind of sums anymore. These are not at all important. It may, like, basically we will be interested in, like, I will not say these are not important at all, but we are just doing here partial derivatives of first order. Okay, but in your syllabus partial derivatives of second order is also there. Okay, that means you know about higher order derivatives, like you find df dx, then d2y or d2f dx2, d3f dx3, you find all those things. Similarly, I'll teach you how to find higher order partial derivative. That means del 2z, del x, del x2 and so on. And again we'll deal with similar kind of chain rules, similar kind of differentials of higher order, and we'll do similar kind of transformation. So that will be much more important as compared to this. So this much for today. Thank you.